Jai Hind everyone. So what is our today's class agenda is we are going to discuss the different properties of fluid which we are going to come across when we are going to deal this subject one by one. So the very first question is how we can define the property. What property is? So property is nothing but it is any measurable characteristic of a system. If you have any system and all the characteristic which we can measure, we call those characteristic as the property of the system. So that is very first thing we have to understand. Property of system is nothing but it is a measurable characteristic. It's very simple. Couple of the basic property of the substances we come across, and we are very much familiar with those properties. That's all. For example, that is pressure. That is very common property which we encountered throughout the fluid mechanics. Temperature, volume, masses, these are very much familiar. We do have the properties which we are going to encounter in the fluid mechanics. Similarly, we have these some other property like thermal conductivity. We have the property like elasticity. We have a property like electrical resistivity. Thermal expansion is again a property of the fluid. Or just a few class back we have gone through another property of fluid, that is viscosity. We discussed a lot of these terms, viscosity, in the previous lecture itself. So these are nothing but these all are the property of the substances. So we are going to discuss, and we are starting with the very first property, that is density. So what is density is? Density is density of any substance is the quantity of matter contained in a unit volume of the substance. So if you have any substance, so how much quantity is going to be contained per unit volume, we could define that is density. So it's a very generic term, we call it density, and we are going to discuss three different type of density characters in the fluid mechanics. Three different way we are going to deal this density. The first density we are going to discuss, that is mass density. So what is mass density? This is nothing but mass per unit volume, mass acquired per unit volume. For any substance we call that is mass density. So what is unit of mass density? You can have a look. That is, we denote this by a Greek letter, that is rho. We are going to denote the mass density by a Greek letter, that is rho. And what is unit? That is nothing but mass per unit volume. So what is unit of mass? Mass per unit volume. What is unit of mass? That is kg. And unit of volume is nothing but meter cube. So the unit of this mass density is nothing but kg per meter cube. And we denote, we are going to denote very often with the Greek letter, that is rho. Now the next density we are going to discuss, that is weight density. We call it weight density. In general, we are very much familiar when we call it density. We can definitely very much familiar with the mass density. We are not talk about any other variety of density like weight density or relative density. So to avoid those confusions, so most of the books, what they use instead of calling this term mass density, they use the term that called specific weight. What we call it is specific weight, and another name is specific gravity. All these terms are exactly same. What the terms? Either you can call it weight density, that is correct. If you can call, and very often you will see in your textbook, the most common name is they are going to use, that is specific weight, or you call it specific gravity. All these three parameter is exactly same. So what is, when you familiar what is weight density? Weight density is nothing but weight per unit volume. The generic definition of density is any substance per unit volume. So when we call it weight density, so weight per unit volume. So what is unit of weight? That is Newton. And what is unit of volume? That is meter cube. So what is unit of the weight density? That is Newton per meter cube, that you can understand. So specific weight is very common term we are going to use in the fluid mechanics, because here the gravity is again going to play a role to any movement in the fluid. So very often we are going to use this term, we call it specific weight instead of calling it weight density. To avoid the confusion, generic term of density is generally is any substance per unit volume that you can classify it. What is the next property is, that is relative density. What is relative density? Sometimes mathematicians, what they do, they use the density of any fluid with respect to some other reference fluid, and that phenomena is very often used in the fluid mechanics. And because we are going to use very frequently, we have to choose the substance as the reference fluid. So two fluid we are going to choose, one for the liquid and one for the gases. Two different liquids we are going two different fluids we are going to choose for the reference purpose. For the purpose of liquid, if we are going to deal with any liquid and we want to have the relative density of that liquid, so we have to choose some reference fluid. So in case of liquid, the reference fluid is nothing but that is water. The different the reference fluid is nothing but it is water. And in the case of gases, so in the case of gases, there is two different type of fluid is very common in use, and most common that is nothing but air. But in some laboratory work, in some research work, mathematicians use also hydrogen as the reference fluid. So if we deal with the relative density for the gases, so most often in our syllabus we are going to consider the air as the reference fluid. But if you go for any research work, you will find several places the relative density is going to be considered as the reference fluid for the gases, keeping reference of the as the hydrogen as the gaseous fluid. So these things we have to understand. So let me define what relative density is. Relative density is nothing but it is density of the given fluid, with respect to the density of the reference fluid. So if it is liquid, so reference fluid is nothing but water. So if you compare for any fluid, what is density with reference to the water? So in general, we all familiar at normal temperature and pressure. It's very close, not exactly same. So I will not call it perfect magnitude, but the sake of reference we choose in our syllabus the density of water is 1000 kg per meter cube. The density, mass density of the water is nothing but 1000 kg per meter cube. So if you have any fluid which density is 997 or 990 kg per meter cube, so if you have the basic idea what is the relative density, that is nothing but it is a density of the given fluid. So that I know that is 990 divided by the reference fluid density is nothing but 1000. So if you can get that is nothing but 0.99. So that you have to understand. This is the way we are going to consider. We are going to compare with the reference fluid. Either that fluid is higher denser compared to the reference fluid or lower denser, that we can find out by this parameter called relative density. So these three density parameters we are going to encounter in the fluid mechanics. The first one is the mass density. The second one is the specific weight. Somehow we can have differentiation. So we have given the different name. Generally that is nothing but weight density. And the third parameter is nothing but that is a relative density that we come across just now. So a couple of the example is given. The relative density of water is nothing but 1. Because if you compare water with respect to water, so obviously the ratio is 1. So water is 1. What is the relative density of the mercury? That is 13.5 or 13.6 close to. It's you can take for your numerical problems as a reference. That can be correct. The third example is also given, that is paraffin oil, which is lighter. The light density is lesser compared to the water. That is 0.8 units. So that you have to understand about these three type of density as the property of the fluid. So what is the next property of fluid? That is nothing but a specific volume. What is the specific volume? What is specific volume? A specific volume is the volume occupied by a unit mass of the fluid. So if you have any fluid how much mass is going to be acquired in a unit volume space. So that we call it specific volume. So you can understand that is nothing but reverse of the mass density. Specific volume is nothing but it is a reverse of the mass density. So what is mass density? That we have defined, that is rho. So if you are to find out the specific volume, that we are going to use the small letter v, that is nothing but volume of the fluid per unit mass. So that is nothing but 1 by rho. So you can get that specific volume is nothing but it is a reverse of the mass density. These are the basic fluid property we have to come across, because we have to easily identify all the properties when we are going to deal the numerical problems in the fluid mechanics. So very, very important to be noted down. Next, that is the coefficient of dynamic viscosity. Generally we familiar with the a term that is called viscosity, as we have gone through this Newton's law of viscosity. We understood what the concept of Newton's law of viscosity is, that we have already gone through. Now we are going to call this term as the dynamic viscosity. Why I call it dynamic viscosity, and what the other variety of viscosity we are going to see just now. So what is viscosity? Viscosity is nothing but it is a internal resistance offered by a fluid layers when they are moving with have some relative motion between them. So that resistance we call it, that property of the fluid we call it viscosity. So if you can go through it, we have derived this mathematical equation in the previous lecture. That is if you try to find out, mu is nothing but tau divided by du by dy. This is called velocity gradient, and this tau is nothing but the shear stress. So because we are familiar with this parameter, generally we call this mu is viscosity, but in exact name of this is nothing but we call it dynamic viscosity. We call it dynamic viscosity. Instead of calling viscosity, we call it dynamic viscosity, because if you recall, when I do the derivation, I just call it is a viscosity, but the specific name is nothing but it call it dynamic viscosity. So what is the unit of dynamic viscosity? You can have a look. What is the unit of the shear stress? That is Newton per meter square. And what is the unit of velocity? That is meter per second. And what is unit of the vertical distance? That is meter. Distance unit is meter. So that is nothing but Newton second per meter square. We also call it Pascal second. So we have seen these units in the previous lecture. Another unit of the dynamic viscosity in the CGS method, that is if you replace the Newton force with the dyne and the meter square with the centimeter square, dyne second per centimeter square, that is unit is become CGS unit, and that also call it 1 poise. It's a name of mathematician who discover or who has justified the concept of viscosity in the fluid. They have do the several mathematical experiment. We'll get some time, we will cover this topic. So this unit is given by this unit is quoted on the name of mathematician is poise. So 1 poise is nothing but it a CGS unit of the viscosity. The next type of viscosity is kinematic viscosity. As we see the previous viscosity mu is, we call it dynamic viscosity. What is kinematic viscosity? Mu per unit density we call it, that we are going to represent with a Greek letter nu. Nu is nothing but we call it kinematic viscosity, which is nothing but it is a dynamic viscosity per unit density. Per unit density we call it kinematic viscosity. So what is unit of the this kinematic viscosity? So we familiar with the unit of this Newton second per meter square. And what is the unit of mass density? That is kg per meter cube. So we have to convert Newton into kg per meter. We have to convert the Newton in terms of the mass into acceleration. So kg meter per second square, and then we can simplify. So when you simplify, you are going to get the SI unit of the kinematic viscosity is nothing but meter square per second. If you convert this meter square per second into CGS unit, that is centimeters square per second. That is nothing but we call it Stokes. So if you relate this meter square per second with respect to the Stokes, so 1 meter per second square is nothing but, if you convert meter square into centimeter square, so that is 10 to the power minus 10 to the power 4 centimeter square per second. So that is nothing but 10 to the power 4 Stokes. So that you can have the basic conversion. It's a very simple. So I explain these units so that you can have the basic conversion between them. So these are very common units. As example, in previous we have seen the viscosity, dynamic viscosity. The most common unit we use poise, CGS unit, because viscosity is by quantity it's very Newton second per meter square is a very big unit. So generally often we'll see in the numerical problems the unit of dynamic viscosity is poise, and similarly in the kinematic viscosity we are going to see the unit as the Stokes. So we should have the basic understanding between the relation between these CGS and the SI units. So what is next? The next property of fluid is compressibility. What is compressibility? Compressibility is nothing but it is just reverse of the bulk modulus. We have seen in the solid mechanics different type of the modulus parameter, that is Young modulus, modulus of rigidity, and the bulk modulus. So this compressibility is nothing but it is a reverse of the bulk modulus. So what is bulk modulus? We can mathematically define what bulk modulus is nothing but. Bulk modulus is nothing but compressive stress per unit volumetric strain, or we can stress by strain. But which type of stress we are talking about? We are talking about the volumetric. So volumetric compressive stress, that we call hydrostatic state of state condition, that we also call it hydrostatic state condition on the particular substance. With respect to volumetric strain, we call that parameter is nothing but bulk modulus. So if you have the basic idea in the fluid mechanics, so hydrostatic stress is going to create in the fluid when you apply pressure, because in the upcoming classes we are going to discuss the Pascal's law. There we are going to understand this concept. So Pascal law, if you apply pressure at any point in the fluid, it's going to equally transmit in all the directions. So that we have to have idea. So what is the bulk modulus? That is nothing but the change in the pressure, that is dP per unit, change in the volume with respect to initial volume, that is a strain. So generally when you compress the fluid or compress any substance, what is going to happen? The volume is going to reduce. Because of that we use minus sign here, so that can be compensated. So this dV is going to become negative, so it's become positive dV by d. So this bulk modulus is a positive parameter. The pressure P2 minus P1, that is the difference in the pressure, divided by the change in the volumetric strain, or we call it volumetric strain, which is created because of this change in the pressure. We call it bulk modulus. So what is compressibility? We are going to denote it by a Greek letter, that is beta. That is nothing but it's a reverse of bulk modulus 1 by K. So you just reverse it, you are going to get that is nothing but minus dV by V divided by dP. This is nothing but we call it compressibility. So that is the basic understanding, because the previous couple of the properties what we have discussed, we have the physical significance of them, what is mass density, what is weight density, or what is relative density, and what are the viscosity parameter we have understood. But what is the physical understanding of the compressibility? The compressibility is going to give you how easily you can compress the fluid. Very simple. If any substance having the higher bulk modulus, it is not easy to compress that particular substance. If you want to compress that substance, if their bulk modulus is high, so it has going to give you much more resistance. So that is a basic understanding of the compressibility. Compressibility parameter, by name itself you can understand that compressibility is nothing but the physical significance of the compressibility is nothing but when you apply the pressure on the substance, what is going to happen? It's going to compress. If the compressibility is high, easily you can compress. If it is low, so you have to apply much more pressure to compress the fluid. It's just nothing but reverse of the bulk modulus. We come across the bulk modulus in the solid mechanics. So what is the Now next thing we have to compare the two different substances, because this explanation is very important in the fluid mechanics, because in fluid mechanics we are going to discuss both liquid and gases as the same, but several properties is very different for both the state of the matter, that is liquid and gases. For example, if you take the viscosity in the liquids, so what happened, if you take viscosity in the liquid, when you start increasing the temperature in the temperature of the fluid, what is going to happen, in case of liquid, when the temperature start increasing, the viscosity start reducing. But that is not true in case of gases. When you deal with the gases, the things is quite different, because you know the molecular collision in the gases start increasing, and because of that, when you increase the temperature in the gases, they are going to offer much more viscous compared to the previous temperature condition. So that the difference, several places we have the behavior of the liquid and gases as different, though we are going to combine this subject as a fluid mechanics, because most of the time we are going to deal the liquid and the gases as exactly same, but the several places they are very much different. So if you see a couple of the points, bullet points is given when we are going to compare liquid versus the gases. So first bullet point is a liquid is difficult to compress and often regarded as being incompressible. So that you can understand, gases has low density. So you can understand, if you try to compress any liquid, it's quite difficult to compress. For example, you can take the water. If you want to change the viscosity, the density of water by just 2%, so you have to change the pressure 100 times. If the viscosity, if the density of the water is 998, it is an experimental data, that is 998.2 kg per meter cube at normal temperature and pressure, that is 1 atm pressure we can call it. So if you want to convert this density become 1001.4 kg per meter cube, this much change you want, it's a quite only few unit, less than a percent. So if you want to change this much density, you have to change the pressure from 1 atm to 100 atm. If you change this much, then only this small change in the density can happen in the case of the water. I take the example. So very oftenly the liquids are incompressible in the nature. Liquids are incompressible in nature, and that's why we call it liquids are very difficult to compress. Similarly, if you say the gases are easily to be compressed and usually treated as such is change volume with respect to pressure. When you apply the pressure, the volume is going to change very significantly in the case of gases. So there is the basic difference between liquid and gases. So a given mass of liquid occupies a given volume, and it will occupy the container it is in and form a free space if the container is of a larger volume. So if that you can understand, if you are going to keep any fluid or a liquid on the container, so it's going to occupy a particular space, that is, it's not often say that if we have a closed room, so if you fill that closed room with the liquid, so the volume is going to be acquired. It's not necessarily that is going to acquire complete volume of the space, but that is not true with the gases. If you release any gas in the control volume, in the particular volume, it's going to acquire the complete volume, and the density is going to be changed very significantly as the volume will keep changing. So that is the another basic difference. As already we talked about the viscosity of the viscosity in gases. So what are the viscosity we have discussed? We have discussed two different type of viscosity. One is called dynamic, and the second one is the kinematic viscosity. So the behavior in the both are quite different, and it's very easily we can classify and try to understand what is going to happen when we take the viscosity for the case of gases. So generally we consider the viscosity with the change in the temperature. So when temperature is going to increase, the molecular collision in the gases is going to increase, and because of that the viscosity of the gases is going to be changed significantly, and it's going to become higher in the magnitude when the temperature is start increasing. So that we have to understand what is going to happen in the kinematic viscosity. If you see, if you increase the temperature, what is kinematic viscosity? That is mu per unit mass density. So possibly that when you increase the temperature, molecular collision is going to increase, that is true. But when you increase the temperature, the density of gases is going to reduce. So this parameter is going to reduce and the viscosity is going to increase. Why? Because the temperature increase, molecular collision is increase, so dynamic viscosity is going to increase, and further the density is going to reduce. It means the kinematic viscosity is going to further increase in the magnitude. The change in the magnitude of in the kinematic viscosity is quite more compared to the dynamic viscosity, that the basic understanding we should have in the viscosity of the fluid. So what happened in the viscosity of liquid if you compare with the temperature? So if you increase the temperature in the liquid, simply the viscosity start reducing when you increase the temperature, because the cohesion force start reducing. Very common example of this, when you have to clean up your cloth, what you do, you use the hot water. So what is going to happen? With increasing the hot water, cohesive forces is going to reduce significantly, and because of that the fluid can penetrate inside the cloth very easily, and so that we have to understand the viscosity is going to play a very important role here. So when you increase the temperature, viscosity is going to reduce significantly, and because of that the flowability of the fluid is going to increase. What is going to happen with the kinematic viscosity? So you can see mu versus divided by the mass density. So when you increase the temperature, mu is going to reduce, but this parameter is going to this parameter is also going to reduce. So both numerator as well as the denominator is going to reduce, and because of that the change in the kinematic viscosity is comparatively low when we compare with the dynamic viscosity. It means when you increase the temperature by a particular amount, dynamic viscosity is going to change much more significantly compared to the kinematic viscosity, because the density is also going to reduce, that the parameter in the denominator is going to reduce, and because of that the change in the kinematic viscosity is quite often less compared to the dynamic viscosity, that we have to understand. So these are the few properties which we have to discuss in today's lecture, which is very important when we are going to discuss in the several topics in the fluid mechanics. So we will stop it here. Thank you very much.